Swayam Prabha. Digital India. Educated India.
Welcome to lecture 32 on time series modeling and forecasting. In the last lecture, we have discussed the extension of univariate time series processes to multivariate case. We observed that if you have time series observations on more than one time series variables, and those time series variables are interrelated, then in comparison to analyzing those time series separately as univariate processes, it may be more beneficial for you, beneficial in the sense that you may get better forecasts, etc., to analyze the dynamic mechanism of all the time series processes simultaneously. A particular time series may be related with its lagged values, its past shocks along with its present shock in univariate time series models, but in multivariate time series models, we also consider that the time series is affected by the other time series. It is related with the other time series and it is affected by the other time series. Not only that, it is affected by the past values of the other time series also. So, that is why we develop different multivariate time series processes. We also discussed the stationary conditions and Wald representation for the multivariate processes. Obviously, for the univariate time series, you can go for frequency domain analysis. Then it may be possible for you to extend the frequency domain analysis for the multivariate case. So, you may consider the spectrum density function or periodogram for the multivariate processes also. In this lecture, we will focus on the frequency domain analysis of multivariate processes. In particular, we will consider the bivariate processes first, and then later on we will extend the frequency domain analysis of bivariate processes to the processes having more than two variables. So, the general case of multivariate processes. So, in frequency domain analysis of bivariate or multivariate processes, we define cross spectrum. So, cross spectrum is an extension of spectral analysis to the simultaneous analysis of two or more time series in frequency domain, obviously. And here your objective is to observe the correlations between two series at different frequencies. In univariate time series, you focus on the frequency domain analysis of a single time series, but here you are considering two or more time series. So, one may be interested in how the time series are correlated, say two time series are correlated with each other at different frequencies. For example, for a particular disease, incidence may be related to certain environmental variables such as rainfall or atmospheric temperature. So, how the frequency of that particular disease is correlated with the frequency of rainfall or atmospheric temperature, or which frequencies are highly correlated, which frequencies are not so highly correlated. One may be interested in this kind of queries. By analyzing the cross spectrum of the time series of disease incidence and environmental variable, we may be able to observe a periodicity in an environmental variable that is ahead in phase of the disease cycle. So, whether the disease or whether the pandemic occurs just after the rainfall, or there is some gap between the rainfall and occurrence of the pandemic. So, one may be interested in studying the phase between in the disease cycle. Now, before moving ahead, first just to remind you, I gave you some of the results of the univariate processes. Say spectral representation of yt and gamma k are given as yt is equal to integral from minus pi to pi e to power I omega t dz omega, where expectation of dz bar omega is equal to df omega. Z bar is the complex conjugate of z. Sometimes we also denote the complex conjugate by z star. So, both the notations are popular. You can use z bar or z star, but here I am going to use this notation z bar for the complex conjugate. Then expectation of dz omega dz bar lambda is equal to 0 for omega not equal to lambda. Then gamma k is equal to integral from minus pi to pi e to power I omega k df omega, which is equal to integral from minus pi to pi e to power I omega k f y omega d omega. Your f y omega is the spectral density function of the time series, and f omega or f y omega is equal to 1 upon 2 pi summation k equal to minus infinity to infinity gamma k e to the power minus I omega k, which is also equal to 1 upon 2 pi summation k equal to minus infinity to plus infinity gamma k cos omega k. So, we have already discussed all these results in the lecture on frequency domain analysis for univariate time series process. Now, we consider cross spectrum analysis for bivariate processes. So, initially we will consider bivariate processes and then we go for the multivariate processes. So, first we consider the stationary bivariate time series x t y t, t belongs to capital T. Then the autocovariance function for this process is gamma k equal to covariance x t minus k, covariance x t y t minus k, covariance y t x t minus k, and covariance y t minus k. or you may write it as gamma xxk, gamma xyk, gamma yxk and gamma yyk. So, in fact, these two diagonal elements gamma xxk and gamma yyk gave you the autocovariances of xt and yt, and then off diagonal elements gamma xyk and gamma yxk gave you the cross autocovariances between x and y. Then the spectral density function for this bivariate process x t y t is defined as f omega equal to f x x omega, f x y omega, f y x omega, f y y omega, and this is equal to 1 upon 2 pi summation k equal to minus infinity to plus infinity. You take gamma k e to the minus I omega k. Omega lies between minus pi to pi. So, this capital gamma k is a 2 by 2 matrix. So, here f omega is also a 2 by 2 matrix. Then in this matrix f omega, you have the diagonal elements f x x omega and f y y omega. These are actually the spectral density functions for the univariate processes x t and y t. So, the spectral densities of the univariate processes x and y are given by f x x omega equal to 1 upon 2 pi summation k equal to minus infinity to plus infinity gamma x x k e to the power minus I omega. Similarly, you may define f y y omega also. Then the off diagonal elements give you the cross spectrum density. Say f x y omega gives you the cross spectral density of x and y. So, f x y omega is 1 upon 2 pi summation over k gamma x y k e to the power minus I omega k. And we have already observed that gamma x y minus k is equal to gamma y x k. So, actually f y x omega is equal to 1 upon 2 pi summation over k gamma y x k e to the power minus I omega k. And then we write this gamma y x k in terms of gamma x y. Say 1 upon 2 pi summation over k, and gamma y x k is equal to gamma x y minus k. And then suppose this the range of k is from minus infinity to plus infinity. So, suppose you replace this k by minus k. So, again you have k from minus infinity to plus infinity gamma x y, you are replacing this minus k by k or k by minus k, and then you get e to the power plus I omega k here. Now, this is equal to f x y omega bar, the complex conjugate of f x y omega, because you have plus sign here. So, f y x omega is equal to f x y omega complex conjugate of f x y omega. Then mod of f y x omega is equal to mod of f x y omega. This you can easily verify. Because So, if you have one number x plus I y, then mod of x plus I y is equal to x square plus y square to the power half. Similarly, mod x minus I y is also x square plus y square to the power half. So, both have the same modulus value. Now, you can also write the cross spectrum as f x y omega equal to 1 upon 2 pi summation k equal to minus infinity to plus infinity gamma x y e to the power minus I omega k equal to say c x y omega plus I q x y omega, where c x y omega is the real part of this f x y omega, which is equal to 1 upon 2 pi summation over k gamma x y k cos omega k, and this real part is called the co-spectrum. And then q x y omega is equal to minus 1 upon 2 pi summation over k gamma x y k sin omega k. This is called the quadrature spectrum. Now, the co-spectrum actually gives you the simultaneous covariance between x and y at frequency omega. Further, the quadrature spectrum gives you the covariance between x and y lagged by a phase pi by 2 at frequency omega. You observe that cos omega is equal to sin pi by 2 plus omega, or cos omega k is equal to sin pi by 2 plus omega k. So, this quadrature spectrum actually gives you the covariance lagged by a phase pi by 2 at frequency omega. Further, in polar coordinates, we can write f x y omega as f x y omega equal to r x y omega e to the power I phi x y omega, where r x y omega is equal to c x y omega square plus q x y omega square to the power half, and this gives you the amplitude spectrum or gain. This is also called the gain. So, this r x y omega is the amplitude spectrum, and phi x y omega is the phase. And then you observe that when both q and c are not equal to 0, then this is simply equal to tan inverse q x y omega upon c x y omega. But if q x y omega is equal to 0, but c x y omega is greater than 0, this is equal to 0, then tan inverse 0 is equal to 0. So, you get 0 here. Further, if q is equal to 0 and c is less than 0, then actually you get plus minus pi here. Of course, you are reaching to 0, but from the negative side. When q x y omega is greater than 0, c x y omega is 0, then phi is equal to pi by 2, and when q x y omega is less than 0, c x y omega is equal to 0, then this is equal to minus pi by 2. Because in this case, this quantity approaches to infinity and tan inverse infinity is pi by 2, and it approaches to infinity from positive side. In this case, this is minus pi by 2. Then amplitude spectrum r square x y omega measures, or this is a measure of the strength of the linear relationship between x and y at different frequencies. And phase spectrum actually determines whether x leads y or it lags y at different frequencies. whether x comes after y or changes in x come after the changes in y, or whether changes in x come before the changes in y. Then now we define a squared coherency. This is a scaleless measure of linear relationship at different frequencies. So, it is just like the correlation coefficient. So, we denote it by rho square x y omega equal to r square x y omega divided by f x x omega f y y omega, or mod f x y omega square divided by f x x omega f y y omega. So, it may be considered as a frequency dependent correlation coefficient. And just like the correlation coefficient, using the Cauchy-Schwarz inequality, you may verify that rho square x y omega also lies between 0 and 1. Then we define coherency or coherence at frequency omega as rho x y omega equal to f x y omega divided by f x x omega f y y omega to the power half. Then this coherency is related to phase and amplitude spectrum by the relation rho x y omega equal to, we write f x y omega equal to r x y omega e to the power I phi x y omega. So, rho x y omega is equal to r x y omega divided by f x x omega f y y omega to the power half. Then you have e to the power I phi x y omega. And this part actually gives you mod of rho x y omega. So, you have mod rho x y omega e to the power I phi x y omega. So, this is how this coherency is related to phase and amplitude spectrum. Now, suppose gamma x y k is equal to 0 for all k. This implies that the two processes are uncorrelated. Now, in that case, you can easily verify that f x y omega is equal to 0. And since f x y omega is equal to 0, rho square x y omega is also equal to 0, because rho square x y omega has mod x y omega in the numerator. Here, rho x y omega has f x y omega in the numerator. Again, we have rho square x y omega equal to rho square y x omega, just like the correlation coefficient. This also you can easily verify. Actually, in rho x y omega, in the numerator you have f x y omega, in rho y x omega you have f y x omega, and you know that f y x omega is the complex conjugate of f x y omega. So, if you take a square, then both are same. Further, we observe that integral from minus pi to pi f omega e to the power I omega k d omega is equal to this matrix. We integrate f x x omega, f x y omega, f y x omega and f y y omega, means we multiply each of these spectral densities by e to the power I omega k, and then we integrate. And then the 1th element is equal to gamma x x k, 2th element is equal to gamma x y k, 1th element is equal to gamma y x k, and 2th element is equal to gamma y y k. So, this is equal to gamma k. Then the covariance between x t and y t is gamma x y 0 is equal to, we integrate from minus pi to pi f x y omega e to power I omega, you take k equal to 0 here d omega. So, this is equal to integral from minus pi to pi, then we write f x y omega equal to c x y omega plus I. So, we integrate both of these terms, and then the integral of q x y omega d omega 0, because q x y omega is equal to 1 upon 2 pi summation over k gamma x y k sin omega k, and if you integrate sin omega k from minus pi to pi, then the integral is equal to 0. So, the integral of this second term vanishes and you get integral from minus pi to pi c x y omega d omega. So, actually this covariance gamma x y 0 is equal to the integral of the co-spectrum. Then just like for the univariate time series processes, the co-spectrum at frequency omega gives the contribution of cycle of frequency omega in the covariance gamma x y 0, or c x y omega d omega. This is the contribution in covariance of the frequencies in the range omega, omega plus d omega. Now, we prove this result. If y t is obtained by applying linear filter to x t, then rho square x y omega is equal to 1. So, we prove this result. So, y t is equal to summation j equal to minus infinity to infinity psi j x t minus j, and expectation of x t is assumed to be 0. So, you have applied this linear filter summation j psi j b to the power j to this series x t, and then you get y t. Then we consider the spectral representations of both of these processes x t and y t. So, x t is equal to integral from minus pi to pi e to the power I omega t d z x omega, and then you can write y t as y t equal to integral from minus pi to pi e to the power I omega t d z y omega, where z x omega and z y omega are random variables such that expectation of the square of norm of z x omega is equal to f x x omega, and expectation of square of norm of z y omega is f y omega, and expectation of z x omega z y omega complex conjugate of z y omega is equal to f x y omega. Further, you can also write y t as y t equal to summation j equal to minus infinity to infinity psi j x t minus j, which is equal to summation over j psi j, and then you write x t minus j. We use spectral representation of x t. So, we write x t minus j equal to integral from minus pi to pi e to the power I omega t minus j d z x omega, and then we interchange the orders of integration and summation. So, we take integral first, then we take e to the I omega t outside here, and summation over j psi j e to the minus I omega j d z x omega. So, expectation of y t x t minus k is equal to expectation of, we write y, the expression for y t from here, y t equal to integral e to the I omega t summation psi j e to the minus I omega j d z x omega here. and then the spectral representation of x t minus k integral e to power I omega t minus k d z x omega, and we take complex conjugate of this. Again you take integral from minus pi to pi e to power I omega k, because this term does not involve z x omega or z y omega. So, you can take it outside the expectation, then again you take summation over j psi j e to power minus I omega j. Again you take this term also outside the expectation. Inside you get expectation of d z x omega d z x omega bar. And remember that the complex conjugate of e to power I omega t minus k is equal to e to power minus I omega t minus k. So, when you write e to the power minus I omega t minus k here, and then you have e to the power minus I omega j here and e to power I omega t here, and you multiply these three terms, then finally what you get? This e to power I omega t will cancel out, you get e to power I omega k here, and then you have e to power minus I omega j. So, you have e to power I omega k here and e to power minus I omega j here. Then expectation of z x omega bar is equal to f x omega d omega. So, finally, you get this result, expectation of y t x t minus k equal to integral e to power I omega k summation over j psi j e to power minus I omega j f x omega d omega. On the other hand, expectation of y t x t minus k is equal to integral from minus pi to pi e to power I omega k f y x omega d omega. Now, we compare the previous equation with this equation. This is equation 1 and this is equation 2, and we compare these two equations, and then we obtain f y x omega is equal to this summation. So, you get f y omega equal to summation j equal to minus infinity to plus infinity psi j e to power minus I omega j f x x omega. Further, y t is generated by the process summation over j psi j x t minus j. This implies that f y y omega is equal to this norm of summation over j psi j e to power minus I omega j f x x omega, or norm of f y y omega square is equal to norm of summation j psi j e to power minus I omega j square, norm of this term square of this, then norm of f x x omega, and then you take square of this. So, you have this result, you have this result. And then from 3 you also observe that say norm of f y x omega square is equal to norm of summation j psi j e to the power minus I omega j square, and then you have norm of f x x omega square. This you get from equation 3. So, making use of all these results, you obtain. So, we obtain square of norm of rho x y omega is equal to 1. So, from this result we observe that if you have two processes and one process is generated as a linear filter of other process, then the between the two processes, say x and y, norm square of norm of rho x y omega is equal to 1 for all frequencies. So, if the two processes have the same phase and the same amplitude ratio, means their amplitudes may be different, but their amplitude ratio remains constant for all frequencies, then the two processes are linearly related to each other, and then they have coherency 1. So, the coherence shows how well these two conditions are satisfied. Now, we consider this example. Say you have the process y t equal to theta x t minus k plus u t, x t follows a white noise process 0 1, it has mean 0 and variance 1. U t also follows a white noise process with means and 0 and variance 1. Further, x t and u t are uncorrelated with each other. Now, we will prove that f y y omega is equal to 1 upon 2 pi 1 plus theta square, f x y omega is equal to 1 upon 2 pi theta e to the power I omega k, and rho square x y omega is equal to theta square upon 1 plus theta square. Now, first we obtain f x y omega. So, this is actually equal to 1 upon 2 pi summation k equal to minus infinity to infinity, then you have gamma x y k e to the power minus I omega k, and then first we obtain gamma y x, then with the help of gamma y x we will get gamma x y also. So, gamma y x L is equal to expectation of y t x t minus L, and then y t is equal to theta x t minus k plus u t x t minus L. Now, notice that x t is a white noise process. So, expectation of x t minus k, x t minus L is equal to 1 if k is equal to L. So, this expectation is equal to theta, and expectation of u t x t minus L is always 0. So, if k is equal to L, or you can say L is equal to k, then gamma y x L is equal to theta and it is 0 otherwise. Then you obtain f y x omega is 1 upon 2 pi, then you have just one term here for L equal to k, and then for L equal to k you have theta here, and then you have gamma x 0 which is equal to 1. And then you can obtain e to the power minus I omega k is also here. Then f x y omega is equal to the complex conjugate of this, which is 1 upon 2 pi theta e to the power I omega k. Then gamma y y L is equal to expectation of y t, and you have y t minus L, which is equal to expectation of x t minus k plus u t, x t minus k minus L plus u t minus L. Now, this product has non-zero expectation only when L is equal to 0. So, this is equal to, for L equal to 0 you get well, theta is also here, you get theta square expectation of x t minus k square, which is 1, plus expectation of u t square, which is 1, and for L not equal to 0 you get 0 here. And then you obtain f y y omega equal to, you get just one term which is corresponding to gamma y y 0. So, this is equal to 1 upon 2 pi, and you get 1 plus theta square, and then e to the power minus I k into 0. So, you get 1 here. So, this is the spectral density for y. So, this is how you get these results, and then you can also obtain the value of rho square x y. The norm of f x y omega, which is theta square, and then f y y omega is 1 plus theta square here. So, this is rho square x y omega. Now, in this example, y t equal to theta x t minus k plus u t, y t lags k time units behind x t. then f x y omega is equal to 1 upon 2 pi theta e to the power I omega k. And then you can write it as r x y omega e to the power I phi x y omega. And then phi x y omega is simply equal to omega k. You can easily verify that r x y omega is equal to 1 upon 2 pi theta, and then you have e to the power I phi x y omega. So, phi x y omega is equal to omega k. Now, is phi x y actually equal to omega k? No, because phi x y lies between minus pi to pi. So, actually phi x y omega is not simply omega k, it is consists of several parallel lines with slope k. Between minus pi to pi, you get several lines, and all those lines have slope k. Now, for the same example, we have simulated 1000 observations from uncorrelated white noise processes for x t and u t, and then we have generated y t as y t equal to 0.8 x t minus 2 plus u t. So, we have taken theta equal to 0.8, k is equal to 2. Then you have the bivariate process. We have plotted the values of x and y here. Then this is the estimated phase spectrum. I had x y 2 pi c, and this estimated phase spectrum is given using z lines. And then we have also plotted, we also observe a sudden decrease at frequency pi by 2. But this decrease can be ignored, because a phase of pi is the same as a phase of minus pi. So, you get a decrease here, but it is because of the reason that a phase of pi is the same as the phase of minus pi. One of the option is to improve the interpretability of the estimated phase spectrum, just add or subtract 2 pi. So, in this lecture we have considered the bivariate time series processes in this lecture, and then we have discussed the frequency domain analysis for bivariate time series processes. Then how we define the spectral density function for the bivariate processes, the co-spectrum for the bivariate processes. Then for two random variables, the extent of linear relationship between the two random variables is measured by the square of correlation coefficient. Parallel to that, we also define a squared coherency for the bivariate time series processes, which is actually a measure of correlation, you can say, or the extent of linear relationship between the two time series at different frequencies. We also observe that if y t is generated as a linear filter of another time series x t, then squared coherency between y t and x t is equal to 1. or if y t and x t have the same phase and the same ratio of amplitude for all frequencies, then again you can express one process as a linear filter of other process, and that squared coherency will be equal to 1. So, you may consider squared coherency as a measure of this phenomena. Then the amplitude spectrum for the bivariate processes is a measure of strength of linear relationship between the two time series, whereas the phase spectrum actually measures whether x leads y or y leads x. So, you can use these two spectrum for measuring this kind of phenomena. In the next lecture, I will consider the estimation of bivariate spectral densities or co-spectrum of the processes x t and y t. For that purpose, we will consider the periodogram analysis, and we will also extend all these results or the co-spectrum analysis for multivariate processes when you have more than 2 time series. So, thank you.
Hello, I am A. K. Sharma and I teach sociology in IIT Kanpur. I am trying to answer a simple question: how sociologists explain their facts. As you know that sociology was developed as a subject dealing with human behavior, but which would use the tools and techniques of science, mathematics, physics, chemistry. But this view that human behavior needs to be studied scientifically has been contradicted later on, and it was said that simply by relating one kind of facts with other kinds of facts, you cannot understand human behavior. To understand human behavior or to actually theorize about human behavior, you have to theorize the theories or motivations or meanings that people have in their mind in involving in a particular action. Now, using these two traditions, one tradition in which we relate one fact of society with other facts scientifically, and another tradition in which we try to develop second order constructs or theories that people have in their mind in acting in day to day life. They have produced two different traditions in sociology. One is called quantitative, another is called qualitative. Quantitative methodology uses scientific methods of conducting surveys, censuses, experiments, and then by using statistical methods, from simple method like arithmetic mean to sophisticated methods like logistic regression, we try to arrive at some inference. Qualitative tradition, qualitative methodology on the other hand uses ethnographic approach, and here the researcher attempts to become part of the community which he or she intends to study, because the assumption is that only by becoming part of the community, by living among the people whom you are studying, and by putting yourself in their shoes, by trying to understand things or their environment or their behavior or their culture or festivals or economic behavior or politics from their angle, from their perspective, how they feel, what understanding they carry in their mind, that only by understanding these things we can understand facts of society. Actually, in one of the latest works, World Bank, which uses a lot of statistics, has also talked about understanding mental models that people use in involving in behavior. Emile Durkheim long back said that sociology uses comparative method, and let me just give one example and then I will finish. Suppose I tell you that infant mortality rate in India is 40. What does it mean? It means nothing. But when you compare infant mortality of India today with Japan, and you find that Japan has 2 and India has 40, then you get disturbed. Then you start thinking, why is it that infant mortality in India is so high? And then you can also compare infant mortality of India with infant mortality of say Kenya or Mozambique or other countries, and you find that these countries have much higher infant mortality than India. And then you can create a hypothesis that perhaps economic development has something to do with infant mortality. Countries which are more developed, countries like Japan, they have low infant mortality. Countries like Mozambique or Kenya, which are less developed, have higher infant mortality. So, you have a connection. This is what sociology is about, connection between facts. So, by using census, surveys, by conducting field work, by using ethnographic methods, by using comparative methods, we arrive at sociological findings. Use of experimental method in sociology has been very less, but I learned that recently economists, which 10 years ago I could not see that economists will one day use experimental method, but today we find that economists are using lot of experimental methods to study human behavior. Now, this work may be done by economists, but the findings of their study can very well be called sociological studies. So, sociology tomorrow, I think that sociology tomorrow, in addition to using surveys and comparative methods, will also be using experimental methods. Thank you.